Welcome to another video on limits. In this video, we are going to discuss about limits at infinity and horizontal asymptote. So the meaning of limits at infinity is as x approaches infinity or negative infinity, where does the function approaches to? So that idea is what limits at infinity means, okay? And then if as x approaches infinity, if the function approaches to a finite value L, then the line y equals L is called the horizontal asymptote of the um, function f of x. Okay, so let's go and find the limit here on the infinite limit. Sorry, the limit at infinity. So here, limit as x approaches negative infinity of 1 over x to the fourth is 1 divided by, so when x approaches negative infinity, and then we take that number and raise to the fourth power, so this is a arbitrarily large number. Okay, so this is a very large number. So 1 divided by a very large number is approximately 0. So that's why this limit is 0. Similarly, this should be a positive infinity here. So if x is approaching to positive infinity, with this same analysis, we get 1 divided by very large number, okay, which is approaching to infinity. So that means this is also 0. Now for this one, we can distribute this limit. So we have limit as x approaches infinity of 2 minus limit as x approaches infinity of sine x over x. So the first limit is just 2 because it's a constant function. For the second limit, we can use squeeze theorem to find this limit. As we did one of the examples in one of the previous video. So this is sine x over x. So we know that sine x is in between -1 and 1. So if we divide by x, which we can do because x approaches infinity means it's a positive number, so we can divide by a positive number in an inequality. So the limit of this left hand side, so limit as x approaches infinity of -1 over x is 0. Similarly, limit as x approaches infinity of 1 over x is also 0. This implies, by squeeze theorem, limit as x approaches infinity of sine x over x is also 0. So that means this limit is 0. So we have 2 minus 0, and that equals 2. Now we have a theorem here which says if this is a polynomial function right here, then we have a couple of things. Okay, so the limit as x approaches positive or negative infinity of x to the n is infinity if n is even. So it doesn't matter whether it's approaching to negative or positive infinity. If x to the n, if n is even, then we still get a positive infinity as our limit. Similarly, if n is odd, then if x approaches to positive infinity, the limit is positive infinity. If x approaches to negative infinity, the limit is negative infinity, because when we raise a negative number to odd power, we get a negative value. That's the reason that we have negative infinity here, okay? Now, 1 over x to the n, in that case, as x, when x approaches positive or negative infinity, that means x is very large number. And then when we raise a large number to nth power, I mean, it is super large. So 1 divided by very large number is 0. So this limit is 0. This is an equivalent expression because x to the negative n is just 1 over x to the n. So that is also 0. And the one important thing that we have here is number 4 here, which says that the limit at infinity for a polynomial function depends on its leading term right here. So we'll just pick the leading term and we'll use this 1, 2, 3 to determine the limit at infinity for the polynomial function. And also it depends on the sign of the constant here. So whether it's positive or negative infinity, that this sign and the exponent determines that. We'll see an example. So here limit as x approaches, let's say, positive infinity of 5x to the sixth plus x squared plus x minus 10 equals, so when x approaches to positive infinity and then we raise that power to the sixth power, we raise that number to the sixth power and then we multiply by 5. So this is arbitrarily large number. So for the polynomial, this leading term determines the limit, and then as x approaches infinity, this approaches infinity because it's arbitrarily large. So the limit is infinity. Similarly, limit x as x approaches negative infinity of 5x to the sixth plus x squared plus x minus 10 equals, so for this one, with a similar argument, we can say, so x is a large negative number and we are raising to the sixth power. So this is a positive number. So here um, that equals to infinity. So similarly, let's go ahead and find the limit for this function here. So limit as x approaches positive infinity of negative 3x to the fifth minus 3x to the fourth minus 12 equals, so here we are, our x is approaching to positive infinity. That means it's a positive number which is arbitrarily large, and we raise to the fifth power, so it's still a positive number, but we have this negative 3 here. So when we multiply this positive number by negative 3, we get a negative number, and it's arbitrarily large number with a negative sign. So that means this limit is negative infinity. So similarly, limit as x approaches negative infinity of negative 3x to the fifth minus 3x to the fourth plus minus 12. So again, this is a large number with a negative sign. So when we raise that to the odd power, we get a negative number times this negative 3 gives us a positive number, and it's arbitrarily large positive number. So we get infinity here. Okay. So similarly, let's look at the third one. So for this one, we can rewrite this as limit x approaches, let's say, positive and negative infinity. This can be written as 3 over x to the 12. So now, no matter whether we put a positive or negative infinity, when we raise that to the even power, we still get a positive number. So 3 divided by a positive number is a um, um, 0, because 3 divided by really large, arbitrarily large number, we get a 0. So this limit is 0. Now let's look at this another example. So we are going to find the determine the end behavior of the rational functions. That means when we talk about the end behavior, that means how does the function behave as when x approaches to infinity or negative infinity. Okay, that's what we are going to look at. So to evaluate the limit of any rational function at infinity, we first divide both numerator and denominator by the highest power of x that occurs in the denominator. So that is the way to find the limit, but there is a shortcut. We'll talk about that. First, let's go ahead and use this technique of computing the limit. Okay, so first let's go ahead and do find limit as x approaches negative infinity of 2x minus 2 divided by x squared plus 10. So the technique is we are going to divide both numerator and denominator by the highest power of x that occur in the denominator. So here x squared is the highest power of x in the denominator. So we are going to divide everything by x squared. So this equals limit as x approaches negative infinity. So when we divide 2x by x squared, so 2x divided by x squared minus 2 over x squared over x squared plus 10 over x squared. Now this equals limit as x approaches negative infinity, 2 over x minus 2 over x squared, and then divided by 1 plus 10 over x squared. Now, as x approaches negative infinity, 2 divided by a very large number, it's a negative number, but it's still a large negative number. So this approaches 0, this approaches 0, this approaches 0. So that means the limit is 0 in the numerator divided by 1, which is 0. Now similarly, I'm not going to do that, but similarly, if we do limit x approaches infinity of 2x minus 2 divided by x squared plus 10, then we will get 0. Now this is the shortcut here. If the degree of the numerator is smaller than the degree of the denominator, that means the denominator um, grows faster than the numerator, and the denominator becomes very large quickly. So that means we are dividing a smaller number by a very large number. So that's why this limit equals to 0. So if the degree of numerator is smaller than the degree of denominator, then the limit at infinity for the rational function, so limit x approaches positive or negative infinity of rational function is 0. And then we have one more thing. If the limit is a finite limit, when we are finding the limit at infinity, if we get a finite limit, then we say that there is a horizontal asymptote for the function. So for this function, the horizontal asymptote is y equals 0. So in the graph, we see that we have a function over here, and then this line is the horizontal asymptote, which is the x-axis. So it means when x approaches infinity or when x approaches negative infinity, the function approaches or goes closer and closer to that line. So the next example here, we are going to do the same thing that we did for the previous one. So we are going to divide everything by the highest power of the denominator, which is x to the sixth. So limit as x approaches, let's do negative infinity. Okay, so when we divide by x to the sixth, we'll get 9 plus 5 over x to the fourth minus 1 over x to the sixth divided by 3 minus 10 over x to the fourth plus 1 over x to the sixth. Now as x approaches infinity, this approaches 0, this approaches 0, this approaches 0, and this approaches 0 because we are dividing finite number by arbitrarily large number. So the only thing that we have here is 9 over 3, and that gives us 3. Okay, so the shortcut for that, now if we do limit as x approaches infinity of g of x, we will still get 3. And you can try doing the same thing, dividing by x to the sixth and then computing the limit. So the shortcut here is if the degree of the numerator, so degree of numerator equals the degree of denominator, okay, then the limit as x approaches infinity, positive or negative infinity, f of x is the ratio of the leading coefficient. So here is 9, okay, divided by here 3, which is 3. That's what we got here. So it is, we usually say a over b, or a sub n over b sub n, okay. Now from the graph, we can see that the horizontal asymptote for this function is right here, which is the line y equals 3. And then our limit is 3. So the horizontal asymptote is y equals 3. Now let's go ahead and find the limit. Let's do the same thing. So if we find the limit here, limit as x approaches negative infinity. Now we do the same thing. We'll divide everything by the highest power of the denominator, which is the x. So if we divide everything by x, we get 2x plus 6 minus 2 over x. Then we get 1 plus 1 over x. Again, this approaches 0, this approaches 0. Now 2x, as x approaches negative infinity, 2x approaches to negative infinity. And then if we add 6 or divide by 1, it really doesn't make any difference. So this limit is negative infinity. Similarly, if we do limit x approaches infinity of 2x squared plus 6x minus 2 over x plus 1, we'll do the same thing. We'll divide everything by x. So we get 2x plus 6 minus 2 over x divided by 1 plus 1 over x. And again, it's same thing here. So this approaches 0, this approaches 0. So as x approaches infinity, means x is a arbitrarily large positive number. So 2 times that number is very large number, which is infinity. Now, here we don't have horizontal asymptote because our limit is not finite. So in this case, usually if we have that, we'll have a slant asymptote. So we see here there's a slant asymptote for this function. So it means as x approaches infinity, the function approaches to that line. And as x approaches negative infinity, the function approaches to that line. Okay. Now to find the slant asymptote, we have to divide the numerator by denominator, and whatever quotient we get, that is the slant asymptote. So we'll just do this 2x squared plus 6x minus 2, and then we'll divide by the denominator here, which is x plus 1. So when we divide, so we'll have to put 2x here, so it gives us 2x squared plus 2x. Then when you subtract, this is 0, 6x minus 2x is 4x. Then we have that minus 2 will bring down. And then we have to multiply by 2. Sorry, we have to multiply by 4. Then we get 4x plus 4. So the remainder is 2 here. When you subtract, the remainder is negative 6, not 2. And then this represents the slant asymptote. So y equals 2x plus 4 is the slant asymptote for this function. So if the limit at infinity is infinity, or if that limit does not exist, so in that case I will have a slant asymptote. Now here is another rational function with a square root. So here we need to be a little bit careful because we have a square root. So one thing that I want to remind you is the square root of x squared is the absolute value of x, which means x, if x is greater than or equals to 0, and negative x if x is less than 0. So for example, if we have square root of 5 squared, the root is 5. Square root of negative 5 squared, the root is negative of negative 5. That's what this says. Okay, if x is less than 0, that means if the number is negative, then we have to put a negative here so that we get a positive root. So in terms of x, that's how we have to write it. So that's something that we need to pay attention here because we have a square root, and when we divide by something, that we need to make sure that we use either positive or negative depending on what we are trying to find. Okay, so let's go ahead and do this one. So first, let's go ahead and find the limit as x approaches infinity for that function. So 12x to the fifth plus 5x squared minus 8 divided by square root of 16x to the 10 plus x to the fourth plus 2. So here when we divide the denominator, we see x to the 10, but it's inside the square root. So basically we are dividing by the square root of x to the 10. So x approaches infinity. Okay, so x approaches infinity, that means x is a positive number. So the square root is just x to the fifth. Okay, so let's write it here. So square root of x to the 10th is x to the 5th in this case because x is positive, okay? Because x is greater than 0 here. So that means we are going to divide the numerator by x to the 5th. So 12x to the 5th divided by x to the 5th plus 5x squared divided by x to the 5th minus 8 over x to the 5th. Everything divided by square root of, but now when we divide inside the square root, we divide by x to the 10th. So 16x to the 10th divided by x to the 10th plus x to the 4th divided by x to the 10th plus 2 over x to the 10th. Now limit as x approaches infinity, this is 12 plus 5 over x cubed minus 8 over x to the 5th divided by square root of 16 plus 1 over x to the 6th plus 2 over x to the 10th. Now when we are finding the limit, so this approaches 0, this approaches 0, this approaches 0, and this approaches 0. So basically we have 12 divided by square root of 16, which is 4, and the limit is 3. Similarly, when we find the limit as x approaches negative infinity, now we have to be careful because we are going to divide by, so when x approaches negative infinity, x is a negative number, so the square root of x to the 10 is negative x to the 5th because x to the 5th is a negative number since x approaches negative infinity. Then in order to get that root, a positive root, we have to multiply by negative. So that's why now this whole thing is a positive number. Okay, so we really have to be careful with this when we are finding this square root, okay, when we have a square root. So now if we divide everything by negative x to the 5th, the numerator becomes negative 12, then minus 5 over x cubed, then plus 8 over x to the 5th, because we are dividing by negative x to the 5th. But in the denominator, we square that and then divide, so it's x to the 10 again, so it does not make any difference. So 16 plus 1 over x to the 6th plus 2 over x to the 10th. Now, when we take the limit, this approaches 0, this approaches 0, this approaches 0, and this approaches 0. So the limit is negative 12 over 4, which is negative 3. So in this case, we have two horizontal asymptotes. One we get from here, which is, so the horizontal asymptotes are one from here, which is y equals 3, and the other one from here, which is y equals negative 3. Okay, so this is negative 3. So equals negative 3. So these are the two horizontal asymptotes. Now, if we look at the graph, we clearly see that x equals 3, the asymptote right here, sorry. It is just a little bit above that, right here. And then x equals negative 3 is the asymptote right here. So that's how we find the end behavior or the asymptote for the rational function. So here is a try now example. You can just pause the video and try this example, which is very similar to the previous one. And then you can check your work by resuming the video. So here, limit as x approaches infinity. So we divide everything by, so again, be careful here. So the square root of x squared is a absolute value of x, which is equal to x if x is greater than 0, and then negative x if x is less than 0. So here for the first case, we are going to take x greater than 0. So we just divide everything by x. Okay, so 8x plus 115 divided by square root of 16x squared plus 10x plus 50. So here x is greater than 0. So that means we'll divide everything by just x. So 8 plus 115 divided by x divided by, so we still have that limit. And then 16 plus 10 We have 10x here, so 10 over x plus 50 over x squared. Remember, in the bottom, we have to divide by x squared because it's inside the square root. Now, when we take that limit, this approaches 0, this approaches 0, and this approaches 0. So we get 8 over square root of 16 is 4, and then we get 2. Now, similarly, as limit x approaches negative infinity, so when x approaches negative infinity, that means x is a negative number. If x is the negative number, the square root of x squared is negative x, because x is a negative number. So in order to get positive, we have to multiply by negative. So that means we are going to divide the numerator by negative x. So when we do that, we get negative 8 minus 115 over x. And in the denominator, we divide by x squared. So this is 16 plus 10 over x plus 50 over x squared. And then when we take the limit, this approaches 0, this approaches 0, this approaches 0. So we have negative 8 divided by 4, which is negative 2. Now the horizontal asymptote are y equals 2 and y equals negative 2. Now if we look at the graph, we clearly see that here is the horizontal asymptote where we have y equals negative 2, and then here's the horizontal asymptote where we have y equals 2. Okay, that's okay. We have one more thing here. So those are the examples we work on. So we have a last term here, which looks obvious because as x approaches infinity, e to the x is infinity, because e to the x is this graph. So as x approaches infinity, the function approaches infinity. As x approaches negative infinity, the function approaches negative infinity as well. Limit as x approaches infinity, e to the negative x is 0, because the graph of e to the negative x is like this. So as x approaches infinity, this limit is 0, or the function approaches to 0. Similarly, for the natural log, so the graph looks like this. So as x approaches 0 from the right, the function goes to negative infinity. As x approaches infinity, the function approaches infinity. So those results are important. We use them a lot. Okay. So that's all for this video. I'll see you again in the next video.